My name's Eric Cunningham. I teach history here at Gonzaga. And at present, I'm the interim director of the Catholic Studies program. I guess I can thank the Catholic Studies program for making what small contributions I've made to this event possible. And for those of you who know the work of Tom Campbell, no introduction is really required. For those of you who don't, and I don't think there's too many people in the room, my students are pretty well steeped in Campbellian lore by now. But for those of you who don't know Campbell's work in any detail, no short introduction would be adequate. So I'll probably just be quiet after explaining how this event came to pass. I was introduced to Tom's work about 3 years ago. And one of my students actually asked me, after one of my world history lectures in which we discussed lucid dreaming and astral projection, I like to talk about all kinds of fun things in my history classes. But this student asked me if I'd ever heard of Tom Campbell. And I said no, but I'm certainly willing to check it out. And I looked at some of the YouTube videos, and this is interesting stuff. Watched it again. I probably logged well over 100 hours of video watching time on Tom's YouTube channel. And then, of course, I had to buy My Big Toe, which I've read now 6 times. I almost hold the record from what Tom says. I'm a little short of the record, but I think I can get there within the next 6 months or so. The short summation of all of this is that I've come to be convinced, and a lot of people in this room figured this out long before I did, that Tom Campbell is one of the great thinkers of our age. I don't know what else to say. You will be dazzled today. What he's done in terms of creating a synthesis between a host of different kinds of disciplines. Not really disciplines, but looking at this human consciousness, digital physics, hyperdimensional reality. I can't think of any thinker alive today who deals with such a diverse range of topics and makes them so intelligible for the average reader. And in doing that, not only gives you wonderful things to think about, but actually projects you outside of your own reality itself. You can imagine my delight when Donna I don't know how it came to pass, actually, but it was decided that Tom was going to make a trip out to the Northwest. And I said, well, Spokane's kind of like the Northwest. So come on out here, and I can get a room for you and take some small steps to put together an event. But little did I know that the event planning was already in expert hands. So again, thanks to all of you for coming out, for Tom to making the trek out to Spokane, and to all of you for showing up. And with that, I guess, and to those of you who came from such far-flung places as San Francisco, Seattle, Hawaii, thank you for making it out here. You know the trip will be well worth it. And for the locals, pay attention. This is rolling down the hill in South Spokane is a small thing compared to flying up here from San Francisco. So all of you, whether you know it or not, are very, very lucky to be here today. And with that, I'll shut up and turn the podium over to Tom Campbell.
Thank you, Eric. And Donna, where's Donna? She's here. Donna in the back. That's Donna Aveni back there. She's the one that said, we've got to go out into the Northwest. We haven't been to that part of the country, and set the whole thing up and made it possible. She and her husband are my organizers, and they do everything, including usually losing a little money on the deal. By the time it's all over, they're pretty good at that too. So they're volunteers, and they do all the organizing. And thank you very much, Eric, for getting this wonderful facility. This is a terrific place to have it, and I'm really glad that it all worked out and I could be here. If while you're listening to me today, you can't see the logic of what I'm saying, that doesn't mean that there is none. It just means that we don't really have time to go into that. If I were to do the whole thing to derive most of the consequences and most of the logic so that you really kind of understood where it was coming from, I'd have to have 3 days, not 3 hours. So I'm going to assume that either you know most of it already, and probably half of you are pretty familiar with my work and do, or that you can go find out later. If there's parts of it that just, where'd that come from? Then you can go back. And the places I'd send you to would be first probably to YouTube, where you can get lots of videos. I've got over 200 videos there, probably 210 by now. And eventually, what you're seeing right now and hearing right now will be on YouTube, probably in a month or however it takes it to get edited and put up there. So if any of that you want to re-experience, you can. And I like to put everything up on YouTube. That's the bigger audience, right? I don't know how many of us there are here, but there'll be probably 10,000 people who will see this by a year from now. So it'll be there. Well, anyway, I've put up videos from New York and from Calgary, and one that I did in Spain that were long 2-day things that kind of go through all the theory in more detail than most people want to hear, and also have a day on Saturday. That would be my Saturday, is the theory. Then Sunday we have a day where we talk about applications. Okay, so if things don't make sense to you, go to those videos and you'll get a lot more. And if it still doesn't make sense to you, the book, the trilogy is 3 books called My Big Toe, and they're available for free on Google Books. You can also buy them in bookstores or Amazon or Barnes & Noble, the usual places, or at my website, but you can find them free on Google Books. So that's where most of the detail will be. Okay. So, and you can find me at YouTube just by going to Google and putting in Tom Campbell or putting in My Big Toe. That's the easiest way to find it. All right. Going to do a little bit of introduction, because there are those that are here that are wondering who I am and why I'm here, sort of thing. And I always do a little bit of introduction for those people, but I'll make it very short. So if you want to know more, then go to my book. The first section in my book is basically an introduction of where I come from, my background, and why I ended up here talking to you. All right, about me. Time frame is early 1970s, okay, 1971, 1972. I get out of graduate school, take my first job, and my boss introduces me to Journeys Out of the Body by Bob Monroe. 6 months later, a group of us from where I work headed out to Bob Monroe's home, which is only about 45 minutes away, and we meet the wizard, who wrote the book. And that was very interesting to me, because like many of you, I was thinking, is this guy making all this up to sell books? Or, did he really have this? Are these hallucinations? What's going on here? Is this for real or not? And I thought if I met him, I'd get a sense of the man as to what was going on. And Bob turned out to be just a very reasonable, very genuine, very nice guy. And he struck me as personality type was engineer. It was all about logic and facts, and turned out that what he wanted most of all in this world was to make these experiences he had, these experiences that he couldn't not have. He tried to not have them, but they just happened to him and scared him half to death. Then he decided, well, if they're going to happen, let's find out what I can do with it. So then he started to work with them, and then he wrote the book. Okay, but he wanted it to be science. He wanted it to be credible. He wanted to understand it. He didn't want to just be this crazy old guy that has these funny things, and wrote this weird book. So more than anything, he wanted to study it, find out about it. And he was looking for some scientists to man a lab that he had just built. And there I sat on his deck that night, and he asked us, anybody want to, any of you scientists, because we were all scientists and engineers, it's the kind of place I worked in. So he said, any of you folks like to come and work in my lab? I just finished it, and I've been a student all my life, so I put my hand up and said, yeah, I'll do it. And another guy who was with me did the same thing. So that was my beginning down this path. Up until that time, I was your usual young physicist out of graduate school. My idea of reality had been, like most scientists, it's called an operational definition of reality. And that is, if you can't measure it, it either doesn't exist or it doesn't matter. The only things that matter are the things that you can measure. things you can do it operational. It's an operational definition of reality. And that's the way most scientists are. Now, by the time I'd met Bob, and I had read his book, my mind was a little more open than that because I had learned to meditate. I had learned to do transcendental meditation and while I was a graduate student. And I found out that it had the curious property that it allowed me to debug computer code. Back then, computer code was a lot harder to debug than it is now. Those are back in the bad old days when we had boxes and boxes of punch cards. And there's lots of things could go wrong, like your cards could be out of order, or the card punch could not punch exactly true in the right spot, besides the fact that your code wasn't right, and you made mistakes in your code. And you only got maybe 2 runs a week because there's a long line at the computer center. There were no such things as personal computers then. And you go put your job in the queue and it'd work its way through the computer center. And you maybe, if you were lucky, got 2 of those a week. So you see, those were tough conditions. You didn't just throw a job in to see what went wrong to help you debug it because you'd never get debugged that way. You had to be very careful with your code. So you spent a lot of hours poring over your code, checking it and double checking it. So when you got that one run that week, it was a good one, you see. So I found out that while I was in a meditation state, I could find errors in my code that I couldn't find otherwise. I could look at my code, it's just like looking at the printouts. I could look at the code and the errors would just jump out. And I could read the lines and I could say, oh, I see, I forgot the semicolon at the end of that sentence. You see, that sort of thing. And then I'd go up to my office, up to my lab, and I'd get out the cards, and sure enough, that sentence didn't have a semicolon in it. So it just amazed me to no end, and it really helped me, made me popular for debugging code in that area. So I knew at that point that reality was bigger than just my operational definition because there was no way to measure me in this transcendental meditation state debugging my software. And I knew it was real because it was my experience. That was my code. I knew it wasn't anything imaginary. So that was kind of my first step into this. Then I met Bob. Then I worked with Bob from that day on. Dennis and I, Dennis Menerick was the other person with me, we went out to the lab at least 3 days a week, sometimes 4 days a week. We go right after dinner. We'd get there about 6:30. We'd get home about 2:30 in the morning. And we were doing that 3 and 4 days a week. So it was a lot of hours. And we did that for about 5 years. So it's a lot of time. And during that time, then Bob taught Dennis and I how to get into the larger reality system whenever we wanted to, on demand. And we spent lots of time verifying it, doing things that we could check on, going to remote viewing. You go look at something and see if that's what you described was what was there, and seeing numbers that were written on a blackboard in another room, and what number was it, and just lots of things that we had to convince ourselves that it was real, not something we were imagining. So we spent probably the first year or 2 doing that. But we were also doing research into what affected altered states. How could we pinpoint these altered states? How could we teach other people to do this? Because if it's just us, then we were just strange people. We wanted to be able to make it so that it was more common than that, more widely spread. And we did come up with a technology, and that's all part of the history. We used binaural beats, and it got to be such a popular thing that we got changed from a research group to a trainer group because there were hundreds of people that said, we want to come to the lab so that you use your technology on us because we're having a hard time doing it without it. So we had so many people coming, and Bob, the businessman, he was a very wealthy businessman. He saw business in the making, so he started setting up seminars, and we built a big, long harness with 20 or 30 headphones connected to it, and then we suddenly were traveling places, giving workshops, and people were coming there giving workshops, and instead of researchers, we became trainers. And after a while, we trained other people to be trainers, and Dennis and I left out, kind of slipped out the back and went on our way. So that's kind of my association and where I ended up being involved in consciousness research. Now, so my consciousness research started at about the same time as my career in physics. okay, because I met Bob soon after I started my very first job. So now I had at least 30 years in both, as a conscious researcher and doing physics for a living, when I finally decided I figured out enough about what was going on in consciousness to write something about it. Then I wrote for about 5 years, probably close to 40-hour weeks of writing for about 5 years, and then I published the My Big Toe trilogy. So that kind of takes us right up to here we are, okay? And all of the talks I give are free on video. Okay, it's interesting to note that I started to write a theory of consciousness, a theory of the larger reality. And it wasn't until the books had been published for, I don't know, maybe 3 years, 4 years or something, I realized that the general principles that defined the larger reality also defined physics. And it just occurred to me, hey, the same idea. Somebody had asked me something. I think it was Ted, sent me an email, and he had something in it. And when I wrote the answer back, the light went on. And I said, hey, this is the answer to the quantum mechanics problem of why particles ought to be probability distributions. I was like, oh, why didn't I see that before? You see? And then just a few minutes after thinking about that, I realized YC was a constant and some other things about physics and the universe expanding and where did the Big Bang start from. And I started doing science then. Well, I'm a physicist. I should have been doing that all along, but I was focused on consciousness. But I found out that the same system, the same concepts were good science as well as good metaphysics. That was very interesting idea. Okay, the theory of consciousness, as it turns out, is very similar in logical structure to Darwin's theory of evolution. We have a very similar structure. This theory of consciousness explains what you experience, who and what you are, purpose, point of your existence, and where did it all come from? Why is it like this? Okay, whereas Darwin's theory explains what you see, kind of in your senses in the physical world, and how did it get to be that way? So very, very similar sorts of structure, logical structure here. Darwin's theory has two assumptions, and I really didn't get this until later. These books were already published before I realized how close the logical process it was between Darwin's work and mine. We went through the same basic thing, and of course that has to do with this being a fractal reality, but that's another story, so I'll get back to this. Darwin had two assumptions. One is that the first cell had to exist. He can take it from a cell, and by cell I'm talking about the initial system that evolved to become what we have now. You have to start someplace. You have to evolve from something. And Darwin said, well, we start with a cell of some sort. All right, then he says, given that, I've got the rest of it. It's going to evolve, it's going to split, I can see why all these things happen, and he worked the whole thing up to where here we are, sitting in, we're the humans at the part of this evolution, and we're sitting here in this hall watching a lecture and listening. So people would ask Darwin, well, where'd that first cell come from? How'd that evolve? And there were two answers to that. There was, well, some people said it came here from someplace else, right? Out of space, landed here from another planet. Well, if you get that line in that answer, then it's like, well, where did it come from on another planet? Well, maybe that came from another planet, but you see where we're going, it goes nowhere. That's an infinite regression that way. So eventually, it doesn't matter really. He said, you got to start with the first cell. But we have some logic that says where that first cell came from. Scientists have put some amino acids and other organic molecules which can evolve just from simple inorganic stuff and put them in a tube and shake it and put a little spark through it or whatever, and they end up with stuff that looks like living cells. So now there's a rational answer. Now, we don't know that that's where that cell came from because, the reporters weren't there with their mics and cameras, to see where that first cell came from. But it makes sense that it just happened. It was random. One answer. That's the other answer, besides came from someplace that came from someplace that came from someplace. So there is a way to describe that. All right, and the second thing that Darwin had to do is he had to prove that there was this process called evolution. Basically, that means natural selection, mutation, and adaptation. All right, now, in consciousness, we start with a vague primordial potential for awareness. That's pretty vague, isn't it? We can call that the first consciousness cell, if you will. The first chunk of consciousness. But we need to start there because we can't tell you where that came from, you see. So we start with that as an assumption, just like Darwin couldn't really tell you where that first cell came from. But we also have some good ideas about where that might have come from, but we really don't know for sure. And that is that there are two new branches of mathematics. By new, I mean in the last decade or two, branches of mathematics. One is emergent complexity, and the other is cellular automata. Okay? Emergent complexity is really a mathematics that verifies or validates the theory of evolution itself. It says that a system can self-initiate, okay, spontaneously evolve, that it becomes something more than just its pieces. And it does that just by random interaction. Okay, just randomly, you have a system. But now it's not just any system. Obviously, if you've got a rock in a box and that's your system, and you're going to sit and look at that rock and see if it will spontaneously evolve, nothing much is going to happen. But if you have a system that has enough potential, that means things like degrees of freedom, complexity, interactivity, it's self-changing. I've done some pieces, and the pieces can go together in different ways, that sort of things. It may be random process, or it may be purposeful. But in any case, that if you have that, the mathematics shows that over time, you'll actually start to build structure. And that structure will try to persist. And sometimes it's successful in persisting. So they're saying that evolution can kind of self-initiate, and they call that emergent complexity. And again, it's not just a thinking experiment, but it's a mathematical process. Okay, the other thing is cellular automata. Now that's another branch of mathematics. It was invented by Dr. John Conway. It's published, you'll find it on the internet if you Google Game of Life, and you can see what it's about. Basically what he found out, his mathematics, was that if you have a very simple rule set, and you let this rule set apply to your system, you end up with a very dynamic thing, and it works like this. You have a board. The way he did it was he had a board like a piece of graph paper, and all the little squares on the graph paper he would randomly color black or white. And then he'd make a little rule, something like if any one square has at least 3 neighbors, any one white square has at least 3 neighbors that are black, then it turns black, you see? And then he'd do that for all the random squares. And then that would change things. Some things that were white would be black, and maybe some things that were black would be white according to his rules. And after everything was changed, then he'd run it again, same rule, and he'd run it again. And what he found in this cellular automata was that, well, he didn't find it, but others who did the research after him found that there were simple rule sets that could generate the properties of general computers. Okay, that means that they could compute anything. They were general computer properties. They found out that there were some patterns that would develop that weren't static. Most of the patterns would just develop to the hidden endpoint, and after that, nothing changed. It was static. But they could develop rule sets that were still very simple, where the patterns never changed. Some of them never repeated. Some of them would repeat. Some of them you have a pattern, and it would destroy itself, but recreate itself in a little different part of the the space. And then it would destroy that one, create another one. What you then had was this pattern that was moving. They were called gliders, that would move across the space. They had patterns that would code information for the pattern and take that with them as they moved. So all these things developed out of this mathematics of cellular automata. So you see, between the mathematics of emergent complexity and the mathematics of cellular automata, it's not that hard to imagine that we get a rule set created by emergent complexity, okay, which initiated a self-sustaining information system with a purpose of reducing its entropy. I mean, what does it mean that things make a more complex thing? More complex means less entropy. Entropy is a measure of disorder. As things make a more complicated or make some kind of pattern, the entropy is reduced. If they lose that pattern, then they basically have degenerated back to randomness again. Okay, so there seems to be this natural inclination to decrease entropy, even amongst very simple mathematical systems. You see? So that's really all we need, because I'm defining this reality cell, defining a cell as a self-sustaining process that persists and evolves. And that's a good definition for a biological cell too. A biological cell is just a process that's self-sustaining, it persists, and it evolves. So we have a mathematical basis here to say, where did this first consciousness cell come? And once we have that, then like Darwin, we can take it from there and evolve that sort of a potential to the consciousness system we have now, of which we are a part. Okay, so what we have is that the primordial consciousness system is an information system. It evolves by lowering its entropy. And that means building structure, complexity, creating useful content. Okay? So structure and complexity, I'm going to go through just a little, very quick logical structure here, and I'm going to take some big steps. So go find it in other lectures, if you will, if the steps are too big. But structure and complexity requires interactive components. Okay, what that means is if you want to build something complex, you need parts. You can't just take a one thing and build something complex with it. The one thing needs parts. Okay, so if we want to reduce entropy, and if that's kind of the natural urge of the system, then what does that mean? That means this one thing is going to have to come into pieces, or it's going to have to duplicate itself and then interact with itself. It needs parts to build more complexity, lower entropy, more significance, more meaning. Okay? So in biology, cells split, and when these cells split, they interacted with other cells. Eventually, these cells figured out that it would be better to cooperate than to just everybody out for themselves. And those cells that cooperated became multi-celled things, multi-celled units. Well, that was more complex. That's a lower entropy. And guess what? It's also more survivable. Okay? Then those cells learned, those multi-celled things, learned how to cooperate with other multi-celled things to make even something more complex. Now you have differentiation of function. Okay, that's an organism where you have some cells that are the digestion part, some cells are the defense part, some cells are the locomotion part. They all had their pieces to do, and now as that group, that's like higher kinds of animals, right? That group was even more survivable, you see, more complicated, lower entropy. All right, in the consciousness part, you have this unitary thing, right? The cellular automata with the rule set that has generated something that we call fundamental consciousness. How does it evolve? Same problem, you see. So this comparison between the evolution of consciousness and the evolution of physical things, it's really saying that evolution is a more fundamental thing. All sorts of things evolve. Technology evolves, right? It's the same thing. Technology evolves with, the very same ideas. The technology that you have, a new technology, has to build on the old technology. And it doesn't have the procreate and survive as its criteria. It has something else. It has how useful is the technology? How much does it cost? How do you price it? What's the demand for it? That sort of thing is its criteria for evolution. So every system has its own criteria. Biological cells procreate, survive. Consciousness, just lower entropy. That's a more fundamental thing, because procreate and survive is lowering entropy, you see? Coming up with more complex technology is lowering entropy. So they're all really lowering entropy, but in unique ways, but consciousness is very fundamental, so it just lowers entropy. That's its goal. Well, if you're going to build parts, then in consciousness, as opposed to technology or biology at this point, in consciousness, these are little parts of consciousness, right? I call those individuated units of consciousness. These individuated units of consciousness, what do they do? Well, consciousness, we said, is an information system. It's about data. It's about information. So what do pieces do? They communicate. So you have pieces exchanging information, being able to process that information, being able to interpret that information, being able to use that information, processing it, making it different, and then sharing it, exchanging it. What you've defined there is a social system, aware pieces interacting. It's a social system. And it doesn't take a lot of thinking to realize that if you have a social system, how do you reduce entropy? Okay, again, this thing's still trying to evolve, right? So how do you reduce entropy in a social system? Well, the two opposite ends are, one, you can cooperate, join together, build something. The other one is it's everybody for themselves, everybody to do their own thing, and that's really hard to build things then. It's really hard to make more complex things as if it's all by themselves. Well, back in the biological world, they did the same thing. These biological pieces, some of them cooperated, made more complex things, more survivable things, but some of them didn't. And what do we call them? Bacteria, right? Single-celled things, billions of them. They're all around. So the single-cell things still exist, but so did some of those single cells cooperate and build other things. Well, so here we have consciousness, okay, that wants to reduce entropy. It has pieces. The pieces interact. It's a social system. And the way that you build and construct is through caring, through cooperation. Okay? And we call that love. It's about other, not about self. That's love. And on the other side, it's fear. Fear is about self, not about other. So those are the two opposite sides. So now we have consciousness as a digital information system evolving with lots of pieces interacting together with the goal of continuing to evolve, of becoming love. Okay, see how that logic drops out? Then the next thing is you need tools. The next thing to happen is that these entities have tools. Well, of course, in the biological, the tools were the claws and the fangs and the fingers and the opposable thumbs and the kind of tools that we generated to help us do things that we needed to do. But if you're a social system of chunks of consciousness, what sort of tools do you need to help you communicate? Well, several things, but they all involve the same ingredients, and that is they involve rules, constraints. Okay, if you don't have constraints, then you don't have any reason that one thing is, better than something else. Everything's just random. The constraints make a game out of it. The constraints give you strategy, they give you purpose, ways to cooperate around, with the constraints. Think of any kind of game you play. The thing that makes the game are the constraints. If you all sit down to play cards and there's no rules, you see, there is no game. The game is made by creating constraints. Certain things you can do with the cards, certain meanings that the cards have, and certain ways that they interact. Those are the constraints. So Now we have tools coming, and what would be a great tool for interacting? Well, language, right? What's language? Language is a set of constraints. Some of these patterns that we talked about that you could generate very easily in cellular automata, some of these patterns could be symbols, could be metaphors, and eventually you'd evolve language with these patterns. Okay, what else could we evolve? The other thing would be a way of interacting, like energy exchange. How can you affect somebody else? And what are the limits of that effect? Rule sets. Anytime you have a rule set, you have defined a virtual reality. A very simple rule set is like Monopoly, right? A Monopoly game, a board game, very simple rule set. Monopoly is a very simple virtual reality. So the rule set defines the virtual reality. Your card game could be seen as a little tiny virtual reality with, say, the 4 people playing the cards, and what the cards mean and what the cards do and how they interact. That's just a little virtual reality. See, so anytime you set up a rule set that allows strategy, purpose, those kinds of things, you've created a virtual reality. Well, now this is a thing that's evolving. So this virtual reality concept's evolved, and you get more and more complex, lower entropy, rule sets that produce more and more useful and interesting virtual realities. And sooner or later, you end up with a virtual reality like the one we live in. You end up with this physical universe as a virtual reality. I know that's a big step for a lot of people to take, and I'm going through this, just the steps I've taken now are usually worth about a half a day, worth of explanation, so I'm going through them quickly. But this is kind of the logical flow that I'm giving you. Okay, well, let's think about that. One question, if you're in a virtual reality, how do you know it? If you're the elf in the World of Warcraft, how do you know about your reality? How do you know? You say, where does this reality come from? So let's say this elf is conscious, and he's going to research his virtual reality, and he has an ability he has access to the data. What is he going to find? He's going to find that his virtual reality didn't exist, and then all of a sudden it did exist. Why? Because one day somebody punched the run button, and that virtual reality started up. It started to run. And then you had this whole reality. And before that, you had nothing. Okay, now, how do we think our universe got to be here? Well, scientists have studied it. They've collected a lot of data and information. And what did they find out? They found out that it seemed to all start with this Big Bang. Okay, there was nothing. There was no universe. But there was, all of a sudden, this little ball, little dot, if you will, a little tiny thing of energy. It was very, very hot, very high pressure, very, very heavy. So you had this plasma, if you want. It's very dense and very heavy. And then at t=0, somebody hit the run button, and it started to expand. And because it had a rule set. One of the rules was that the mass involved, had certain properties, right? It pulled together, and then the force from this bang blew it apart. Well, the pulling together and coming and blowing apart ended up making this universe. As it cooled, suns coalesced, planets, all the rest of it got trapped, going around suns and so on. So we end up with a universe. And what was that? Where did that initial ball that it started from come from? Well, those are just initial conditions. That's what you set up. Those are the initial conditions. That's the rule set. You push the button, t=0, and it starts to expand and go. Okay, so our universe just popped out of nothing. Where did that concentrated ball of energy come from? Who put it there? Well, certainly it didn't come out of our universe, because our universe didn't exist yet. Our universe hadn't even started to expand, so it had to come from someplace else, right? It just started. Sounds like a virtual reality. That's the way virtual realities start, just like that. Okay, I call that the digital bang, okay, because it's the start of the computation. Okay, so basically we have a rule set. It evolved, and it evolved into this physical reality that we have. Okay, it's dynamic. That means it changes with time, right? It's dynamic. There's in all virtual realities, there's time, even in Monopoly. There's time. You make sequential moves in Monopoly, and every time somebody moves, that's one tick of the Monopoly time clock. And somebody else moves, and that's another tick of the Monopoly time clock. Well, in this, you have this virtual reality, and there's a outer time loop around all the code that defines it, and every time you increase the time by delta t. Then you go through all the calculations, you get back to the beginning. When you're done, you increase it another delta t, make all the calculations, and that's this outer time loop goes around, and that's how simulations are done. That's how we create virtual realities. That's why the elf in World of Warcraft moves. It's because there's a clock that every, hundredth of a second, thousandth of a second, that elf's position gets recalculated. Okay, and if the time, if the resolution is fine and the time is fine enough, you see that as smooth motion. You don't see that as little jerky motions, but it is at the tiny level. All right. So we've come a long way here in just this one slide. The reason that there's two things that kind of pop out here. The first is that one of the things that physicists always have wondered about, and they still wonder about, but you and I know that the reason that c is a constant, c being the speed of light, is because this is a virtual digital reality. And what happens is that we have this little delta t. So t keeps, every time you calculate, you get another delta t. And delta t is a constant. It wouldn't do to have delta t being big and small. That way we go really fast, then we go slow motion, then we go really fast again, and that wouldn't work out. So it's a constant. That's the way we do our simulations. Then you have a little pixel of volume. Okay, we know pixels on our screen, right? And pixels in our cameras, and they're little chunks of area. But now think of a three-dimensional pixel, which is a little pixel of volume. Okay, the idea, how small is that pixel? Well, that would give us the resolution of this virtual reality, how small that pixel is. Now, if your monitor or your TV had pixels of different size, what would happen? Well, if you had a whole lot of real dense pixels here, millions of pixels here, but over here there was just one big pixel. It was about 6 inches on a side, right? And over here they were smaller and bigger. Your picture would be real crazy. Well, it wouldn't be a very good reality to learn in. So all the pixels need to be the same size. That makes everything stay consistent. Okay, good reality for these individuated units of consciousness to use. So how fast can you move information through this reality? Well, you can move it 1 pixel every delta t. You can't move it from this pixel to that pixel all in 1 delta t, because now you're teleporting, and again, your reality becomes very squirrely. You have to go from pixel to pixel to pixel to pixel, and that's as fast as you can do it. So if you move it 1 pixel every delta t, you can't get any faster than that. Well, that's the speed of light. Speed of light, a speed is a distance per unit time. It's a pixel per delta t cycle, you see? So that's why light speed is a constant. It's as fast as things can go here, 1 pixel at a time, and that's a big mystery. Physicists know that it's a constant, but they don't know why. And for that matter, it can vary some, not quickly, not from time to time, but over generations. It can change some, and why would it change? Why would this velocity of light change? And of course, we know that it does change some. It has changed some. And the reason that one might want to change it would be that we may need more resolution. You know how that is. Back in 10 years ago, when your resolution, you thought it was good when you bought it and it was new, and then 10 years later, the resolution's really poor, right? It isn't good enough anymore. Why? Because you want to do things at finer and finer level. Well, same with this virtual reality. Somewhere in around the early 20s, it became obvious that we were on the threshold of starting to measure things smaller and smaller and smaller in time increments that were tinier and tinier. Our technology had gotten to the point that we could do that. We ended up from microscopes to electron microscopes. And we ended up with electronics that could measure nanosecond distances in time periods and things. So right around that time, they noticed a little change in C because we got better resolution. Well, at least that's a good guess. I'm guessing at why that happened. Well, what would you do if delta x over delta t is velocity of light? You'd want more resolution in delta x, which means you'd want to make that smaller. And you'd want more resolution delta t, you want to make that smaller. And if you made them both smaller by the same amount, c would still be the same, right? So if you have this fraction and you divide the numerator by 10 and then you divide the denominator by 10, the fraction's still the same thing. But this is digital. You can't divide it just by any number you wish to keep them the same. They're digital. You can only change delta t by chunks of delta t. See, you can't divide a delta t into decimal points, into places. You can't do a fraction of a delta t. You got to do it in whole chunks. And it's the same with your resolution. You do your resolution in chunks. So because they're digital, you can't divide them. It's hard to make them come out exactly the same, but you can get them really pretty close because these things are small. So what we find is that C seemed to change in around that time down in the fifth decimal place, fourth or fifth decimal place. And nobody knows why. So that might be the reason. This is conjecture on my part. But anyway, the other thing is that there are two ways to approach this virtual reality. One of them is through probability, okay, probability-based simulation, and the other one would be through let's say a particle process. In other words, there's two ways of looking at how our reality is built. There's a top-down, which is the probability way, and there's the bottom-up, which is the particle way. Now, they both give you the same whole picture. It's like if you get a picture of a dog and you started at the nose and you added in pixels all the way to the last pixel was the tail, or you started at the tail and added in pixels all the way to the nose, two different processes, but you end up with the same dog. Well, here, if you have a reality, there's two ways to build it. You can build it from the bottom up. You start with particles, subatomic particles. You start with, the littlest things make the next bigger thing. Okay, subatomic particles then make atomic particles. Atomic particles, of course, make atoms. Atoms make molecules. Molecules make small chunks of stuff. And then more molecules make bigger chunks of stuff. Okay, that's from the bottom up. That's the particle theory of the way reality is. From the other end, you start at the top. Now, this is the way virtual realities are all done. Virtual realities are all probabilistic models. You start at the top, and you have a rule set, of course, and the rule set will define, what you have. So let's say we have rule sets. We'll start with something simple like Newton's laws, right? That's part of our physics or rule set. Okay, so the way things move, and two things can't go through each other, and there's space, and so this is the way. So you just compute effects, not necessarily causes of effects. Now, we do this all the time in our virtual realities. If your elf in the World of Warcraft runs into a tree, what happens? He bounces off. If he runs into it fast enough, he gets hurt, right? If your character in The Sims gets in a swimming pool and his nefarious brother or sister pulls the ladder out of the pool, what happens to your character? He drowns because the game says if you don't have a ladder, you can't crawl out of the pool, and if you stay in the pool for so long, you drown. Okay, so those things happen. Now, that's not because the Sims character's lungs fill with water and they no longer have oxygen in them and so on. He drowns because they are modeling the effect. Stay in the water too long, you drown, right? Jump off a cliff in World of Warcraft, you get hurt if the cliff is too high. And if it's really too high, it kills you. So they're modeling effects. The elf isn't made up of molecules. They don't model the elf's molecules to produce the elf. They model the elf and his effect and how he interacts with the rest of the world. Basically, Newton's Newton's equations, right? It's all this interaction boils down to. Those are pretty simple. That's back when physics was simple and easy. Okay, so you do that. So that's the virtual reality. It's probabilistic. What is most probable? When that elf runs into the tree, how hurt is he? Well, it depends on how fast he was running and how big the tree was and things like that. You do some calculations, but then it's just probable. You're not into the molecular notion, and we aren't here either. It's just modeling effects. Okay, it's a much simpler computer science problem to model our reality, okay, as an effect, as probability. That's easy. If you model our reality from the particle bottoms up, it's horrendous. You have to keep track of every particle and every particle's interaction with every particle until you build up something, like this stand here or me. Now you're talking about billions and billions of particles, just to do this one little piece of wood here that the computer has to keep track of all that stuff. Well, obviously, no computer model ever does that. That's silly. It takes billions and billions of billions more computer processing to do that than it does to just model the effect. Okay, so if you're going to make a virtual reality, you'd do just like The Sims and just like the World of Warcraft people. You'd model it statistically. You'd model it from probability. You'd model it from the effects that happen. Okay, well, that's the way ours is. Now, the way that works is that each player in this virtual reality gets a data stream. Okay? Every player in World of Warcraft gets a data stream. They're sitting at their computer, they've got the mouse, or the joystick, the keyboard, and they get a data stream to their monitor, to their computer that shows them what's going on and what their elf is doing. So does every other player. Well, this virtual reality works the same way. Each of us, we are consciousness. We're not these physical bodies. These physical bodies are like the elf. These physical bodies are our avatar. We are an individuated unit of consciousness. We're those little pieces that we're interacting with each other, chunks of consciousness. This body is our avatar, and this body is just information. It's just data. Just like the elf's body is just data. Now we reach out, we put our hand on this and say, well, this seems pretty solid. Would data be this solid? But if you've ever played The Sims, you know that the Sims character puts his hand on the table and it's solid too. His hand doesn't go through it. Why not? It's a rule set. The rule set says you can't let that happen. See? The Sims character can get up on the table. Sims character can jump on that table and dance. He doesn't fall through the table just because the table is calculated. He's calculated too. You see? It's all calculated and there's a rule set. So it is with us. We live in a virtual reality. And this virtual reality sends a data stream to each of us, by us being the individuated unit of consciousness. That's who we are. We take that data stream and we interpret it into what we see. We interpret it into our sense. That data stream is our sense data, what we sense. Okay? And this is how we interpret it. Same with the elf. Same with the Sims. You get data, and your computer takes that data and interprets it to a display on your monitor. And that's how you know what's going on in the game. Okay, well, how did we learn to interpret this data? We started when we were born. We learned what things were. As our eyes began to focus, we had to learn what everything was. That's how we learned how to interpret this data. Trial and error, by doing. Wasn't that we got taught. It wasn't that it was hardwired. We had to learn it. Well, now we grow up, we know how to interpret the data. We can tell the difference between an apple and a doorknob because we learned those things. We learned the symbols for the language. We learned the metaphors of our culture. It took us a long time. We're still learning it now. But you learn it, and then you get the data, you interpret it. So that's how we came to be here. Now remember, in this logical process, why are we here? So that we can interact, to lower entropy, to become love. So you see, now we have an idea of what our purpose is, what the point of us being here is, what's the point of this virtual reality. So the way it works, like I say, is that the character gets a data stream. Now what data stream do they get? Well, they get the data stream that they require from instant to instant. So if your elf looks to the right and sees the woods are the data that's sent to your computer. If he turns his head to the left and looks, and there's the mountains are in his data stream. So the data stream represents his senses, right? Each individual gets their own data stream. What that means is that the data stream is given according to the character making measurements. Right? The character makes a measurement. It's a measurement when you open your eyes and look toward the mountains. That's a measurement of what's over there to the left. Mountains is the answer. So the character, the avatar, requires data according to what he does, the measurements that he makes. And we will see in a little bit that this turns into what's called the measurement problem. Because when we look at this at a very fine scale, it tells us without any hesitation that reality is a virtual reality. And that's what the measurement problem is about. You look at a very fine particle, and you realize that the particle doesn't actually exist. This is what the double slit experiment tells us. The particle doesn't exist until you make the measurement. Why? Because it's too small for you to see, so the measurement isn't sense, right? It has to be an instrument that makes this measurement. Well, when that measurement's made, suddenly there's the particle. Before that measurement was made, it was just probability. And that's what's confused scientists about the double slit experiment now for almost 100 years. Well, it's obvious, that's the way it works. It's a probabilistic simulation, and until a character makes a measurement, nothing gets rendered. You see, it's very simple to understand. And if you'd like to talk about double slit later, I've got some slides, and we can go through it if you'd really like an explanation, more detail how that works. We can go through. But in other words, modern physics has shown us that indeed we have the characteristics of a virtual reality. From the very small, okay, which is like double slit experiment, actually all of quantum mechanics tells us we have a virtual reality, to the very big, okay, everything has to do with measurement. One way that you can think of the way the probability works is that every measurement, every choice, every time you open your senses to see something, there is a probability of what you'll see. And it's probability based on two things. One, historical consistency. What happened before, right? You can't walk out your door one time and be in the desert and walk out the door an hour later and you're in the jungle. It doesn't work like that. You need historical consistency. So if there was a microphone on my stand now, and I look away and I look back, there's going to be a microphone on my stand now, because the probability of that microphone being there, the next second is 1, because it's there. You see, that's historical consistency. Okay, but now we do something that we have a lot of uncertainty about, then those probabilities aren't 1. Okay, now let's say I'm going to measure, I'm going to look at a big telescope, bigger than anybody's telescope's ever been, and I'm going to look farther into space, and I'm going to see a new piece of space that nobody's looked in before. And when I look at that piece of space, there might be 100 different things that could be there and still be consistent with everything else that I know. Because maybe I looked in this part of space and this part of space, but I've never looked in that part. But what's in that part has to be consistent with these other parts. You wouldn't expect something just in a different part to be totally different. So it's constrained, that it can only be certain ways because of the constraints of what we already know. But within those constraints, there may be 100 different ways that it could be configured. Well, when I look through that telescope, I see something. The system has to send me data, right? My senses now looked. I'm owed the data. What am I going to get? How does the system do that? Well, they take all the things that are probable and they put them in this distribution, which means some of them can be more probable than others. Okay? They're not all the same probability, but they're all in this big distribution, and the ones that are most probable, carry most of the distribution. The ones that are less probable or less likely to be pulled, it randomly pulls out 1 out of that distribution of all the possible things that don't conflict with what we already know. That's what you see. It's a random draw from the possibilities. Now, after you see that, the next person who sets up to the telescope's got to see the same thing. Then it's a probability of 1 that he's going to see that because that's already come into this reality. And those of you familiar with double slit realize that that's exactly the same way it works with little things. You measure that particle turns out to be an electron or a buckyball or some other particle that's being thrown at these slits, and once it's measured, it's a particle from then on. It travels in a straight line, just like a particle ought to travel. You see, it can't do anything else. So whether it's a big scale, whether it's a tiny scale, or anything in between, our physics keeps reminding us that this is a virtual reality, and that the best way to describe this physical reality is as information. When I started in this, after I published these books, I did a lot of researching. Of course, you should always research before you write books, but I research after I write books. What I was writing on wasn't something I expected, to find anywhere else, so I researched afterwards, and I found that there was just 2 other people on the planet, as far as I know, that gave credence to the idea that this reality was a virtual reality. Okay? It wasn't very popular. Today, it's almost standard physics. Your average physics guy is pretty well convinced that this reality is best described just by information. I was listening to a video on YouTube of some professors who were at CERN looking for the God particle, Higgs boson. And there was just an interview, and he was trying to explain to these people what he was doing and why he was doing it and the significance of it. And one of the things he said, they asked him about particles, and he says, we used to think of electrons as little chunks of mass that had charge. That's the way we used to think about them. He says, and then we thought about them as probability clouds. And he says, now we find that what we think an electron, it's a point. It's not a mass, it doesn't have extent, it's just a point, and it has the properties of mass and the properties of charge. He says, that's the way we look at electron. Well, what is a point with the properties of mass and charge? That's just information, right? It's just information. If you had a virtual reality and you were trying to make a simulation of an electron, what would it be? It would be a point with the properties of charge and mass. So physics has come almost entirely. I wouldn't say that it's totally mainstream yet. It's still a little bit on the edge, but they are really coming around to the idea that this reality is just information. That means it's a virtual reality. That means it's a computed reality. If it's a computed reality, there's one fact about being a computed reality that's very interesting. A simulation cannot compute itself. It has to be computed somewhere else, because this is like 3rd grade logic, right? The simulation that hasn't been computed yet can't compute itself because it hasn't been computed yet. You can't compute yourself. So that means that there is a place from which it's computed. And the idea is, well, who's the programmer, and where's the computer, and that sort of thing then becomes a big question, and science does not want to go there. That's a place they don't want to go. And that scares them half to death to go there. So they're now in this odd, awkward phase of saying, yes, it's a virtual reality, but I don't want to talk about it. I really don't want to talk about that because somebody's going to ask me about, well, where does it come? Who's computing it? And I don't want to go there. And I know that's funny, and you say, well, how could they do that? They're scientists, right? But I watched, and you can watch too, on a video of a major physicist. These were top schools. MIT had a guy there, and CERN had some people there. They were all of Europe and the US, top physicists, and they were on a panel discussing virtual reality. And all of them were convinced that reality was virtual and that it was information. And the idea was brought up. Yes, but what about this other? Where did it come from? Don't you realize that, if you have a virtual reality, it can't compute itself? That one physicist who said that. All the rest of them on this panel, which I think there was like 6 or 7 of them on the panel, all the rest of them kind of looked at each other and said, well, we don't really accept that, and let's change the subject. That was sort of the result. They didn't, they said they didn't really accept that, but then they didn't really want to talk about that either. So that's kind of where we are now in physics. It's being more and more accepted that this is a virtual reality, a computed reality that's best described just as information, but we're not really ready to go any further than that. And there's good reasons for that. We can talk about that later if you want to talk about that. Okay, so there's 2 other things I want to tell you. This slide's kind of overrunning its timeline, but two other things I want to talk to you about. And one of them is that in order to produce this virtual reality, you need some infrastructure. Okay, obviously you need a computer, right? You need a time loop, and you need a rule set. But besides that, to be efficient, you need to keep some databases of what's going on. Well, we have 2 major databases that help make this thing work. One of them is what I call the future probable database. And that is a projection of everything that could possibly happen and the probability that it might happen. Okay? So this delta t is very small. So you're just guessing one more delta t ahead. Well, delta t is somewhere around 10 to the minus 44 seconds. So see, that's really small. We can't measure anything nearly that small. So if you only had to guess what was going to happen 10 to the minus 44 seconds from this instant, that would be pretty easy. We're not even going to move in that amount of time, you see. So it's pretty easy to say. And then you say, well, if that was right, what about the next delta t? And if that was, assuming that's right, what about the next delta t? And you're going to work your way out that way. Of course, the further you go, the rattier your results are. Because each time, if one of your first guesses was wrong, then that wrong propagates out with each layer, because now the second layer is based on the first, and the third is based on the second. But you can do that, and that's what I call the future probable database. Everything that could possibly happen of any significance, right? We're not going to keep track of, trivial things, but everything of any significance happens, and the probability that it'll happen. Okay, take it out just as far as it makes sense to you. Eventually it gets really ratty, so you quit. The other database is really derived from that database, and that is all the action, and the action is in the present, where we, individuated units of consciousness, are interacting with each other with free will, making choices. And those choices we make are choices that are out of an intent of love or of fear. So they're choices that help us evolve or make us de-evolve. So that's what we're here for, to interact, to learn, right? To lower our entropy. Remember, that's the whole point of the whole system. That's where we're going. And we make choices. Interaction, this is our game, right? It's like the Monopoly game, except a lot more detail. So we're in this game and we make choices. And based on our choices, other things happen. As we do things that it affects other people. Other people doing things affects us. We're all affecting each other. And that's where the action is. But then after that delta t's gone and we're on to the next one, the last delta t becomes history. And there's 2 parts to this history. One is what I call our history thread, and that's everything that we actually did, all the choices we made. But then there's all the choices we could have made, but didn't, and the probability that we would have made them. You see, it's just the same probability was up there in the future probability, was unactualized, and now becomes a past probability with the probability that, we would have made that choice. So it's the same data, really, that's in the future probable, passes through the present. The action is we make choices, and then that data falls into the past. So these are 2 big databases. It's actually just kind of one database that moves from the future to the past. But anyway, so that's an idea. So that'll tell you that the future probable database, it's not a done deal. It's just probable. It's an interesting thing, though. We can modify that probability with our intent. We can change that probability of what's likely to happen with our intent. Okay. How does that work? Well, that's part of the feedback mechanism. Why are we here? We're here to grow up, to learn, to become love, reduce our entropy. And that's part of the feedback. We get to create the world we live in. We can modify future probability with our intent. All right, I talked about the telescope idea that it's a random draw, but I'll talk about one that's in the middle, kind of a medium-sized thing, and we'll talk about oxygen molecules. Does our virtual reality computer have to render oxygen molecules for us to breathe in this room? No. Who of us can see an oxygen molecule? We don't have any sense data that gives us oxygen molecules. Our data stream doesn't carry any information about oxygen molecules. Okay, well, what if we had a microscope or some kind of thing that could see them? Yes, they'd have to be rendered, but only on that microscope sample. Certainly not here in the air. Well, does that mean that we really don't need to breathe oxygen? We're really not breathing oxygen? Yes, it does. Well, how is it that if somebody held our nose and mouth shut, we would suffocate because we wouldn't get oxygen? Well, that's because right now the probability of there being enough oxygen in this room to support our life is close to 1. There is some small probability that all the oxygen molecules in this room would all go up into that corner. And we'd be left with nothing but, nitrogen and a couple of rare gases and things, and we'd all suffocate and fall over, but it's very unlikely. That's about 10 to the minus 36. Yes, people do those kinds of calculations. That's about 10 to the minus 36 that's going to happen. It's not likely. Okay, billion's only 10 to the 9, so, 10 to the 36 is small. So the probability is that we have oxygen here. Why is that probability good? Near 1? Because there's still enough forests, there's enough plankton, there's enough trees and things that, there's enough air conditioning, there's enough windows or whatever, vents. All of that says that the probability we have enough oxygen in here is pretty good. So when we take a breath, that's like sort of a measurement, right? Is there enough oxygen in here? And you pull a random number out, and the random number is always close to 1 because that's the way the probability is here. So we breathe, we get along fine. So you have a system that is modeling not from the ground up, not in terms of molecules, but in terms of events, in terms of, what happens from the top down with probability. And the last one I think I already talked about was a double slit experiment, and that's where you have a barrier with 2 slits in it. You send particles at it one at a time, and you find out that the particles, you would think, if their particles are really particles, you expect them to go through one slit or the other slit, and they pile up behind this slit or they pile up behind that slit. And that, in fact, doesn't happen. And they send particles now. They started with light, photons, and then they went on to electrons, and then they went to hydrogen atoms. They went to bigger thing. The biggest thing I know of, they've done an experiment with a thing called buckyballs, which is like a soccer ball arrangement of carbon atoms. It's 60 carbon atoms. As molecules go, it's a pretty big molecule. And they throw buckyballs at this thing. It works the same way. Well, what do they end up in? If they don't pile up behind the slits, they pile up in what's called a diffraction pattern. It's a pattern of light and dark areas where they hit here, but they don't hit here, but then they hit there, but they don't hit next, and you get these little lines of light, little spots of light, or little slits of light behind the slits. Why do they do that? Because particles aren't particles. They're probability distributions. The probability gets to the 2 slits, and there's some probability to go here and there. There's some of the probability goes through both, because it could go through either. So the probability isn't like a particle. A particle has to go through one or the other. Probability can go through both. Okay, so the probability goes through both, and then that probability that went through each one, they interact with each other, and when they do, some places there's a high probability of being hit, and in other places there's a 0 probability of being hit. So you get this pattern on the other side. This is the double slit experiment. Well, then they decided to look at the slits and see what's going on there. So they did measurements at the slit. And they put a little measuring device at each slit, and they said, aha, there goes a buckyball, or there goes an electron. And what happened when they did that? Every time they measured what slit it went through, they ended up with a pile behind this slit and a pile behind that slit. They didn't get a diffraction pattern. Why? Because they did the measurement. When they got the measurement, the system gives them the data that defines the particle. That particle just began existence as a particle right there from a probability distribution, and when it did, all it can do then is act like a particle, travel in a straight line. You can't diffract or do anything sexy like that anymore, because now it's a particle in this reality. It has to stay here in this reality, you see, as a particle. So they stop doing the measurements, they get a diffraction pattern. They start measuring again, they get 2 spots. You know, and then they did something else that was even more amazing. They measured the data, but they didn't look and see the screen, what's on the screen. But you measured it, and you know that screen is going to have piles of particles behind each slit, okay? Because that's what happens when you measure it. And then before they looked to verify that, they erased the data. And then they looked, and they had a diffraction pattern. You see? So that then made everybody double take. Well, the reason for that is when they erased the data, there's no longer any historical data here to be consistent with. It's back to being probability. There is no constraint now that it has to be a particle. No measurement's been made. Therefore, it's back to probability. So that's how that works. And quantum physicists right now don't understand that, but it's a very simple solution, you see, to their problem. And it also explains all the rest of their quantum events, like tunneling. Tunneling is a thing, you put a particle in what's called a potential well. All that means it's a box it can't get out of. It just doesn't have the energy to get out of the box. But what they found is that they get out of the box anyway. Why do they get out of the box anyway? It's because when you take that random draw, most of the time, it's something that's likely to happen, which is stay in the box. But sometimes when you take that random draw, it comes out from under the tail of that curve, right, of that distribution. And then you get the 1 in a million happens, and that particle gets outside the box. Well, we don't notice that generally, but with particles in boxes come in the billions of particles, right? You pump that box full of atoms, you have billions of particles in there, and if they 1 in a million that you find them outside the box, you kind of find a bunch of them outside the box. So that's a tunneling thing, and we have tunneling diodes that are part of all this electric equipment here, and it works just on that principle. So these are facts of physics that tell us that our what do we call it, the materialistic view, or we all sometimes call it material reductionism, which means everything's reduced down to smaller and smaller particles, that this materialistic view just isn't right. We violate it. So anyway, that's where we're going. I got to jump on here. These are a few words that I haven't talked about. I just want to go over them very quickly. Decision space is I'll just give you very short definitions. Decision space is all those choices that you know you have. That's your decision space. Okay, something happens, I'm going to make a choice. I could do one of 10 things. Now, I really could do one of maybe 30 things, but I don't know about any more than 10. Because of my beliefs, because of my fears, because of other things, I only see 10. That's my decision space. Okay. Now, free will says you have the choice of one of those 10. Nobody tells you which one of those 10 to pick. That's all free will is. Sometimes people imagine that free will means you can get anything you want. It's like a genie in a lamp, with as many wishes as you want, but that's not free will. Free will is simply you get to pick which of those choices that's in your decision space. And that's entirely possible for that idea of decision space and free will to be generated in a computer, in an information system, where you have a certain finite choices and you get to pick one. Okay, well, we already talked about an individuated unit of consciousness. Love, we mentioned, the opposite of fear. It's about other. Fear is the opposite of love. It's about self-focused, leads to entropy increase. Ego, now that's one I'll spend a little time on. Ego is the awareness in the service of fear. You can have awareness that's not in the service of fear. It's not like you're either blotto and you're totally unconscious, or you have ego. It's not like that. You can use your intellect your awareness in the service of love or caring. And that works fine. But when you use it in the service of fear, we call that ego. And you think, well, that's a really different definition than what Freud had of ego, but it's not. It's actually the same. And I see you got handouts that everybody got. These definitions are in detail in your handouts. That's why I gave you those, because I'm going to go over these so quickly that if you haven't been to this material before, I'd probably leave you scratching your head. So the handouts are to give you these definitions in detail. I talk about a being level versus intellectual level, and the reason I'm telling you these, I'm going to use them later on, so I want you to know what they mean. And that is, I pull us apart. This is kind of an arbitrary boundary, but I pull us apart into two pieces, and that's the intellectual level. That's what we think. Okay, that's our thinking part. And the being level, that's who we are at the core. And those two obviously are not always the same. So that's what that is. Now, morality, good and evil, that's a measurement in entropy. If what you're doing, if your intent, and intent drives action, if your intent is something that's going to decrease your personal and system entropy, that's good. Because that's why we're here. That's that's why IUOCs, that's why we exist. That's why this virtual reality exists. So if we're playing the game and we do something that decreases entropy, that's called good. We do things that don't, or that increase entropy, then that's bad. So the difference between the dichotomy between good and evil is the dichotomy between you lowering entropy, which is good, that's toward love, or increasing entropy toward fear. Okay. So now we have kind of a scientific definition of love. What is it? Love is is a consciousness, a very, very low entropy consciousness. That's what love is. Okay, and the last thing that I'm going to talk about is open-minded skepticism. Okay, what that means is you stay open-minded, accept all data, but you have to be skeptical. Okay? Neither one by itself is very useful. If you're only open-minded but not skeptical, you're liable to believe anything, things that aren't true, things that are dysfunctional. Okay? And the idea is you don't really want to believe anything. You want to always just be open-minded and skeptical. But if you're only skeptical and not open-minded, well, we call that closed-minded. You're shutting out data because you know it can't be true. And that's very bad. So just open-minded or just skeptical, neither are functional. You need to be open-minded and skeptical. And what that means is you need to learn to live gracefully with uncertainty. Because when you're open-minded and skeptical, there's a lot of things you just don't have enough information on. There's a lot of things you just don't know. And that has to be okay. If you really need to know and have an answer to that, what you'll do is you'll make up a belief, and then you'll pretend that you know it. I call that pseudo-knowledge, and then you'll say, okay, I feel better now. But basically, you've just put yourself in a trap, because now you've shut yourself off from certain information that conflicts with your beliefs. So open-minded skepticism is important. Okay, how the world works. Very simple little rule about how the world works. Stuff happens, we get to deal with it. That's the way it's always worked. It worked like that when you were born. It works like that now, and it's going to work like that when you get old. Stuff happens, and you get to deal with it. Unfortunately, we tend to focus on the stuff that happens, not how we deal with it. And what we do with the stuff that happens is that we focus on how are we going to manipulate it? How are we going to make that stuff that happens be the way we want it to happen? And almost all of our energy is focused on that. What we need to focus on is how are we going to deal with it? And why are we going to deal with it? What's our intent? What's our motivation in dealing with it? What are we trying to accomplish here? Okay, if we focus on that, now we're focusing on what's important, because that choice is what either lowers your entropy or raises it, makes your decision good or evil, you see? So you need to focus on the choice you make. how you react. So if something happens, somebody insults you, how are you going to act? You can get mad, you can throw something, you can cry, you can get upset, or you can just smile but be, inside. You got all these things that you could do. These are all choices in your decision space. Or it could be none of those. You may think about, why is that person upset like that? What is, they must have some sort of problem. There's some issue there. I wonder if I could be of any help to solve that. What could I say or do that might ease that and make them feel better? You see, now you've made a choice out of caring for other. And that's a choice towards your growing, to your evolving the quality of your consciousness, which is what we're here for. So that's kind of what's going on there. So right choice, moving from self-focused, fear-based choices to other-focused, love-based choices, that's what we're here for. And you find if you do that, everything works better. All right, now why does it work that way? What's the mechanism that makes it work that way? Well, here's a fact you may not have thought about, but if you do think about it, you'll find it's a very simple concept. There's more negative, unproductive choices than positive, productive ones in your decision space. Always. It's easier to destroy than build. There's more ways to do it wrong than to do it right. Okay? For instance, let's say you've forgotten your significant other's birthday 3 years in a row. You're in trouble, right? You've done something wrong here. Now, how are you going to fix it? Well, there's a whole lot of things that you could say and do to make it worse. Almost an infinite number of those. But what are the things that you could do that would make it better? There's only a few of those. So there's just a couple of ways that you could do something that would make it better. There's lots and lots of ways that you could make it worse. It's always like that. So building and doing it right requires more skill and effort, more knowledge than doing it wrong. Doing it wrong is easy. Just to give you a little example of this ratio of the number of wrong choices in your decision space versus the number of right choices, let's just take a real simple little example. We'll show how that works out. Take a child's jigsaw puzzle of 10 pieces. Okay, there's a puzzle that's got 10 pieces, and we'll say each piece goes in one of these 10 places, and each piece could be rotated in this, or this orientation, right? And that's it. So you got 4 orientations and 10 of each piece and 10 pieces. Well, what that says, if you got 10 pieces, each piece could go in any one of the 10. So there's a 10 by 10 array there. It's 10 squares. You get 100 chances of getting it. If you pick up one and stick it in a place, only 1 in 100 is in the right place. All right, now if each one has 4 orientations, that's 1 in 400. Now, what's the probability that if you pick one up and you put it in place number 1 and it's going to fit in place number 1, and the second one that you pick up is going to place exactly right in number 2, and so on? These are random picks, like you're just randomly picking from these pieces. Well, then that would be 1 over 400 times the 10th power. And you know what that is? That's 100 billion ways to do it wrong, and one way to do it right. Okay, so you see how quickly the number of wrong choices grows and the number of right choices is very small. Okay, so just kind of run down that list. Fear is reactive while love is proactive. Okay, being proactive requires understanding, empathy, caring. Okay, ego is self-focused in a little picture, and it's much simpler than love, which means others. You have to understand others, their issues, their problems, their needs, and it takes a lot more than just doing what's good for yourself. Okay, belief, pseudo-knowledge, is easier to come by than actual knowledge. Pseudo-knowledge, you just have to believe something. That's easy. Real knowledge requires experience, rational thinking, research, trying to get data, and often you can't get all the data, so you're left with uncertainty. You have to live with that. Being open-minded or skeptical is easier than being open-minded and skeptical. So you see how this is working. Pretending or assuming certainty is easier than accepting uncertainty. Okay, so there's many ways to create a problem, only a few ways to fix it. So intentionally evolving the quality of your consciousness, doing what I've been talking about, what it is we need to do, what our purpose is, why we're here, that's usually the path less taken because it's a lot more effort. It takes effort to do this. Being dysfunctional is easy. You know, being dysfunctional is easy and simple to do, but the life it creates is difficult and complicated, and just the other way around. Doing the right thing and decreasing entropy takes a lot of thought and effort, but the life that it creates is very simple and joyous and beautiful. Okay. So spiritual growth is the same thing as increasing the quality of your consciousness, is the same thing as evolving positively, same thing as eliminating fear, becoming love, lowering the entropy of your consciousness. All of these things are symbols and phrases that mean all the same thing, and they all require focus and effort. Okay. And there's only a few ways, much fewer ways to do that than there is to not do it. All right, now. Okay, so now we get to the point of why does it work that way? And I'm talking about the stuff that happens and you dealing with it. Okay. When you're manipulating the stuff that happens to be the way you want it, which is what most of us do all the time. We try to manipulate our boss, and we impress him, and we flatter him, and we do all those things so that he will do what we want. We manipulate our others, our children, our husbands, our wives. We try to arrange it so that everything will work out the way we know is best, right? And it's work out the way we want it, according to our mostly to our fears and our ego. Okay, but though we think that's a grand vision that we have for the world, and it's the way the world should be, the way we'd like to manipulate it, it turns out that's a grand illusion. And why is that? That's because your information is subjective. Now what that means is we have an idea, well, if I do this, then they'll do that, but everybody has their own data stream. Everybody has their own reality. And what I think about something isn't necessarily the way somebody else is going to think about it, particularly if that somebody else is very different than me, particularly if that somebody else is the opposite sex of me. We're liable to have misunderstandings. What I intend isn't necessarily what they get, or if that person's from another culture, or if that person is much older or much younger than me. You see, they're going to interpret things very differently. So here we are manipulating away. We're going to do this. It'll cause them to do that, which then will be good for us. And we're lost from the beginning because those other people aren't going to react the way we think they should, the way we would, because they're not like us. The second thing is that we have no way of knowing how our manipulation is going to work out in the long run. How is what I do going to change things 10 interactions down, a year from now, 10 years from now? Say I'm interacting with my child. How is that interaction going to affect that child 5 years from now? You see, we don't know. Now, we know that if we were in that child's place, it wouldn't affect us very much, but that's not necessarily the way it is from the child's point of view, you see. So here we are. We really don't know how anybody's going to take our very clever manipulation, and we have no idea, even if we did know, what that would amount to. All these bumps that we're going to get, later, we have no idea where it's going to go. So what's that mean is we're making these decisions based on almost no information. The information is only based on ourself, the way we think it ought to be, and the way we think other people react, and the way we think their interactions might go, and that's only maybe 2 or 3, minutes or hours down, and not 10 years down the line. So we're really going blind most of the time, and what have we decided? There's just a few ways to do it right. There's all these ways to do it wrong, and we're just guessing. What's the likelihood that we're going to guess those few ways that are going to happen right when we really don't have any information? And what's the likelihood we're going to start pushing on those ways, those much larger set of ways that are dysfunctional. You see, it's almost impossible, just from the basic logic of it, for you to manipulate the stuff that happens to happen the way you want it. It's like putting too many clothes in a suitcase. If you put this shirt sleeve in, something pops out of the other side. You just can't get there because you don't have the information. You don't understand the way other people see. You don't have the information of where it's going in the future, the effect it's going to have. And if the person, like I say, is the opposite sex, a different culture, not near your age, your chance of getting it right is very small. So that's why it doesn't work well. That's why if you spend your time trying to manipulate the front end, what you create is misery. You create unhappiness. You create things that don't work. Relationships don't work. Most of us go through life with a struggle. We're constantly struggling with life, constantly trying to make it be more the way we want it, and it never seems to work out. Oh, maybe it does for a little while. No, we're happy, but it doesn't last very long. It always then goes to hell in a handbasket very shortly thereafter. Well, if she would just learn this, if she could just get rid of this problem, life would be great. That's the way we think. The problem isn't her, it's you. You see, it's a different perspective. And that's why it works that way. We're very unlikely to get it right if we're just trying to manipulate from our fear and from our ego. So what we should do is pay attention to how we react. How we react is important because now we can focus on doing it right for the right reason, not on manipulating where we really don't know what we're doing. That grand vision, like I say, is a grand illusion and almost guaranteed to always get it wrong. All right, so that gets us to how do I grow up? How do I get it right? Okay, we have a couple of fears, and one of those fears is if I don't constantly work to make good things happen for me, everything would go to hell, in a handbasket almost immediately. It's only my constant effort to manipulate things to be the way they want them that makes my life even, livable. It's not all that good anyway. It's a big struggle. That's a fear that gets in the way of us. Once you get rid of that fear, and you can just do things that are right for the right reason and let what happens to you happen to you, you find that things don't go to hell in a handbasket. They actually get much, much better. Everything starts to work for you. Your relationships get better. Everything gets better for you. So, but it's the fear. You have this fear that if I don't try to make it come the way I want it, it won't. It'll be awful. That's number one fear. But you got to let go on. When you learn to focus on making good things happen for others, then good things will happen for you. But it requires for you to be able to be at ease, graceful with uncertainty. You see, you have to have that ability. And otherwise the fear will rule what you do. Okay, so what should you do? Well, try to become a low entropy bubble of big picture understanding. Okay, so if you are a low entropy bubble, that means you're about love, you're about caring, you're about other people. You're not about fixing it for you. You're about helping other people do what they can do, as much as they can do, and that makes you a low entropy bubble of big picture understanding. You understand the game. The game's not about manipulating stuff to be the way you want. The game's about about the decisions you make and the quality of those decisions. Okay, so you have to eliminate the fear that we just talked about, the ego, the beliefs, and the way you do that is find the fear. Many of us have no ideas about all the fears that drive us, about how much of our life is driven by our egos. We just don't know that. Well, what you should do is every time you feel anxiety, anger, something just doesn't feel good, anytime you get something that I'd call a negative feeling of any sort, there's a very, very high probability that that's because you're interacting with your ego, and ego is a derivative of fear. So you find that feeling of, this doesn't feel right, I didn't like that. This upsets me or whatever. Fine, why am I upset? Why am I angry? What's really the issue that makes me angry? And don't just stop at, well, because I wanted my way and didn't get it, that's pretty obvious, that's ego. But why do I need to have it my way? What's pushing this direction? And you will find a fear, because I'm afraid that if I don't, I'll get run over, or I won't get what I'm due, or somebody else will take what belongs to me, or you have these other fears. And once you find the fear, then you have to overcome it. Now, that's easy to say and hard to do, but the only antidote I know of for fear is courage. You have to want to overcome it. Remember, we said this is not an easy thing necessarily to do. It takes work and focus. You have to think about that. And every time you feel that fear, and that stuff happens, you need to not react to it. You need to think about what you're going to say, what you're going to do, how you're going to react. Take charge of that and do it with love. And that's how you find and get rid of the fears. That's how you grow up, because the ego is obvious. That's not hard to, it's not hard for us to see the ego that we're using when it's all about us. But realize that ego will lead you to a fear. Ego is just a result of fear. All right, so that's how you do it. But be open, use open-minded skepticism. Don't be foolish. Learn to live gracefully with uncertainty. Embrace life. Be proactive. Get involved. Do, be, explore, find out. You can't do this in a cave. The idea of becoming spiritual isn't to go find a quiet place and sit down and get up into an altered state and stay that way. That might feel good for a while, but that's not really how we learn. We learn by interacting, by being, by dealing with people, making those choices. And the more we get involved, the more opportunities we have to do it right. And the more opportunities we have to do it wrong, but that's where you have to use your focus and your intent. You want to do it right. You have to really want to, or it won't happen. Okay, so how do I do it right? How do I right wrongs? How do I make the world a better place? A lot of people get to that decision. They say, this world is really terrible. The wars, the hate, the ego, it's all over the place. How do I make this world a better place? What can I do? Unfortunately, we tend to almost focus on something else as the problem. Oh, I know the problem. It's the political system. It's the economic system. It's the food system. It's always something else. And if we could fix that, then everything would be all right. That's not the case. You can change the politician, you can change, lots of facts, but it really won't make big difference in the long run. It only makes difference in the short run. If you want a long run change, what you have to do is get to the cause and not try to fix the symptom. You see, that bad politician that is forcing evil on us all, that's a symptom. That's not the cause. The cause is high entropy. The cause is fear. The cause is ego. So what you really need to do is lower the entropy of the system. And how do you do that? You have only one thing that's for sure that you can do that, and that is lower the entropy of yourself. Because if you lower the entropy of yourself, that will affect everybody else that you meet. Everybody else will be pulled up just a little bit because you've pulled yourself up. That will help. And that's the only thing that will help, because if you replace that politician or that leader, that president or that whatever, if you replace them with somebody who's kinder and gentler, it'll only last for a short while. It will eventually go right back to the way it was if the people don't change. In other words, our politicians, our institutions that we complain about are just representative of us. They're full of fear and ego and what about me and greed and all that stuff, because we are, right? They're one of us. It's just one of us that's gone up there. The only difference is that when they do something out of fear and ego, it has big effects. When we do something out of fear and ego, we holler at the wife, kick the dog, tell the children to be quiet and that kind of thing, because it's all about us. So it's just a little bit of misery we make, whereas people who have a lot of leverage can make big misery. But it's all the same people. They're like that because we're like that. And it's whether they're elected or not isn't the point. It's not they're like us because we elect them. They're like us because they're part of our culture. They're part of us. So if you really want good government that works, then you need to have people in it who are all about love and caring, not about themselves and ego and fear. And the only way to do that is if the people are about love and caring. And if the people are about love and caring, then so will be the institutions. You see, they'll change all by themselves. You don't have to go up and have the revolution and depose this guy and put somebody else in that you like better, because that'll all degenerate right back to the way it was shortly. What you have to do is change yourself. And that's the beginning. Because when we change, everything else works fine. So we have all these competing economic systems. We have the capitalist system, and then we have a socialist system, we have a communist system, and we fight with each other over those systems. But no matter what system you have, if it was populated by a bunch of people who were very low entropy and all caring and loving, in the institutions, out of the institutions, they would all work. What's happened is any one of those systems would start to change to optimize itself for the people, because they'd be based on love and caring, you see. So no matter what you start with, it would change to be something that would work really well. And the reverse happens too. As long as we're full of fear and ego, no matter how we shuffle the chairs on the deck of the Titanic, it's going down just the same. No matter how we shuffle things around, we pull out this leader and do that, and we do those kinds of things, and we institute new and better laws and so on. It all is going to end up representing us being the way we are, because the people in the institutions are just like us. And if they're full of fear and ego, then that's what you're going to get, no matter how good your thoughts were to begin with. So the point is, how do you change the world? You start by changing yourself. Now, does that mean that you shouldn't care about the world? No. Get involved, Go demonstrate. That's part of education. That's part of helping other people see bigger pictures. Talk about it. Join a club, join a party, do whatever you want to do. But you have to do it not from we're going to win, we're going to beat those people, but we're going to share. We're going to give them information, something that's useful to them. It has to be a positive giving thing, not a beating, violent kind of thing. So that's the thing. Sure, get involved. Sure do. But it's all about being. Why you do it. It's the intent that counts, not so much what you do. Okay, now, so that's kind of the first part that I was talking about, which was how do we, the way forward. So the way forward is how to be and why it works, and why trying to manipulate will never work, no matter how clever you are. It just won't work, because there's a million different ways to do it wrong and only a few to do it right, and you really don't know what the hell you're doing when you're trying to manipulate, because you don't understand what people are going to get, how it's going to affect them, anything else. Very, very high probability it won't work well. You just think it will. You hope it will. And we spend our whole lives trying to make that work, and people spend their whole lives struggling, always with their relationships, with everything else. And that's why. That's kind of the science of it. All right, we're going to change the subject now. Where are we going? Where are we headed? Okay. Belief is not a good thing, because belief keeps you from looking at all the data that comes in. Because once you believe something is true or false, data comes in to the contrary, and you discount it. False data. People didn't know what they were talking about, you see. So that puts up a wall around you. I call that, belief blindness. So belief blinds us. Okay. The major belief in our culture today, the thing that has trapped most of us, and we don't even think of it as a belief, is a belief in material reductionism. A belief that this reality is only this physical universe, and that's it. Okay, we define it as this physical universe, and its reductionism means we define it from the subatomic particles up to us. And that's the way it is. And we believe this. Why? Because it's part of our culture. Well, we also get taught that in school, but we believe it just by osmosis. It's part of the culture. We get it from each other. all consciousness is netted. That's why when you grow up, you help everybody else grow up, because all consciousness is netted. But if you get in with a lot of people who have a belief, you're kind of pulled into that belief as well. So you have to always push the ball uphill. You see, it always takes effort and focus to grow up. It's easy to roll downhill with the crowd. Anyway, so that makes our scientists the new high priests. You see, the belief in the land of material reductionism is a belief in science. It used to be that the high priests were the people who told everybody else what was right, what was true, what to believe, what not to believe, right? That was the high priest function, is to give guidance to the people about what was good and not good. Well, now, who do we go to find out what's true and what's right? It's the scientists. If we want to know what to think about something, scientists will stand up and say, well, here's the way it is, and we believe it, because they're the high priests, and we have confidence, and they wouldn't tell us that if it wasn't true. Okay, that's the way it is. Now, the problem with that is that material reductionism has so many holes in it, so many things now, that they're logically incompatible with life experience. For instance, the placebo effect. Everybody's aware of a placebo effect. Well, if this reality is materialistic, then how it is that you can have two groups of people, one's your study group, the other is just a group that gets nothing, just to see what happens to them. What's that? Control group, right? They're the control group. And you take the group that's the study group, and they have ailments, and you give them sawdust pills. I don't like to say give them sugar pills, but sugar's not good for them, but I hate to say things that would hurt people. Anyway, you give them some kind of innocuous pill that has no medicine in it whatsoever, but you tell them that it's a wonderful medicine, it's new, and it has great history of being effective and so on. And about 35–40% of the people that are given that good news about this fake medicine, their ailments will get better. Whereas in the control group, who are not told anything like that, they don't get better. They don't have that same thing. So the placebo effect is statistically, verifiable effect. Well, in a material reductionist philosophy, it's impossible. What are those little molecules? Why do the little molecules, and the subatomic particles change from that conversation about the value of these sawdust pills? You say, well, there should not be any effect there. But there is. PEAR Labs, P-E-A-R, Princeton Engineering Anomalies Research, they do experiments for mind over matter. Intent changes the results of statistical processes. They've done this for many, many years. Impossible. Remote viewing. A lot of studies have been done on remote viewing now. It's gone past the stage of, is that real? We know it's real. The CIA thought it was real, years back, and so do other foreign country governments, and it is real. Lots of research. A material reductionist can't happen. Telepathic communication. How many times has a mother known that her child was hurt? Lots of times. How many times did you know that somebody, what somebody was going to say or not say, or what might happen? And you say, yeah, sometimes it is a good guess, but sometimes it's obvious it's not a good guess. You got information. What do we call that? Oh, that's your intuition. Oh, well, that's okay, intuition. But in a material reductionist philosophy, you can't have an intuition. There is no such thing as intuition. It doesn't belong unless you can explain what intuition has to do with molecules and subatomic particles, you see. Lots of things. Expanding universe, space. What does the universe expand into? If this universe is all the reality there is, how do you get a bigger universe? How do you make space? What does it move into? What was there before, it expanded into something, right? And how does that work? You see, this philosophy can't tell you. All the quantum mechanics, double slit experiment, entanglement, all of those things can't happen if you have a materialistic or a material reductionist philosophy. None of these things are allowable. Consciousness is a hard problem, right? The reason it's a hard problem is because it's an impossible problem. They think consciousness has to be the result of molecules, has to be the result of material things. And it's a hard problem because nobody has a clue how to justify that assumption. And it's unjustifiable because consciousness is not created out of mass, the particles. They can't justify it because it just isn't true. We don't even know in physics what mass is or why it is. We don't know what gravity is. Why should masses attract each other? We don't know. Okay, it's a mystery. It's not about the molecules. You see, these are things that don't fall into this material reductionism. Charge is the same way. We don't know what charge is or why it exists. Space, time, intuition, tunneling, synchronicity. I mean, the list goes on and on and on of the failures of our dominant scientific belief to provide answers. So what's that say? That says that there's something wrong with the assumption, right? That it's not correct. Okay, well, physics has been moving away, away from this material reductionism very slowly, very begrudgingly. They've been embracing virtual reality, but it's only a new thing, only over the last, 5 or 6 years. But they're doing it in faster and faster. Almost every week I get something on the internet or somebody tells me about some other group of scientists that say, yay, verily, it's just information. Reality is virtual. Okay, so the first big paradigm shift is well underway. That's our reality is a VR. It's a virtual reality. We're past the tipping point there. The tipping point was probably about almost a decade ago, and then after that, and the reason it's that way is our experiments have just been dragging scientists kicking and screaming into that realization. Okay? Now, the next big paradigm shift is other. And we talked about that. A virtual reality doesn't compute itself. Simulation can't design and execute and compute itself. So that'll be the second big step, big paradigm shift. After that is once we say, okay, there is a VR, okay, there is an other, and now that the other is consciousness. See, there's going to be a big food fight once we realize that there's other. Everybody who has a stake in other, claiming it, what comes to mind first would be all the religions, right? They're going to say, told you so. There's another, we're here, there. I know who the programmer is and so on. So you're going to have all of the religions plus other groups are going to want to claim other for themselves. Oh, other belongs to us. You see, there's going to be this big tussle of who gets to own other when we get to that one. So that could be noisy, loud, and even violent when we hit to that paradigm shift. All right, the next paradigm shift after other becomes acceptable is that consciousness, is the computer. When that is other, that other is consciousness, okay, and that it's a finite, natural, evolving digital information system, then we will be on our way. The second is that once we know it's consciousness, is that consciousness evolution is the goal. It's our individual and collective purpose. Okay, and the last thing is that consciousness evolution is toward becoming love, that love is the answer. So you see, we have all these steps, which are big steps, but if we can get through all those steps, what are we left with? We're left with a cultural belief not in material reductionism, but in love is the answer. That's what we have to go to. We're here to evolve the quality of our consciousness. Now, wouldn't that world be a different world than where we are now? Wouldn't necessarily be perfect because a lot of people have a lot of things to learn, but wouldn't it be nice if everybody kind of realized that that's what the game was about? That would be pretty magnificent. So that's kind of the paradigm shifts. That's where we're going. All right, now a little perspective on how we might get there. Okay. Remember I talked about become a bubble of enlightenment? Throughout history, there's been lots of these bubbles of enlightenment. Lots of them. Some well-known examples would be, Buddha, Lao Tzu, Greek and Roman republics, various political and religious leaders, Gandhi, Martin Luther King, Nelson Mandela, lots of, these are big names, right, that everybody almost in all cultures knows the names of these people because they embraced love and caring rather than what was easy, which was force and fighting. But there's also lots of little bubbles of enlightenment, individuals. And it may be just a little old lady who lives in the corner house who's so sweet, helps everybody out, and always has a little plate of cookies for the children, that kind of person who just cares about people, wants to give. It doesn't have to be somebody leading their people to freedom, It could just be individuals. They're all little bubbles of enlightenment. And I'm sure just in this audience, there's probably, half a dozen people here that fit that category. They're bubbles of enlightenment. They're helping everybody grow up because of their own example, because they're growing up. So that's good. Historically, these bubbles have been isolated. Individuals. It's very hard to talk to people. You're excited about these ideas and you talk to your friends and your neighbors and the people at work and they look at you like you're insane. They laugh at you, and pretty soon you're the weird person who's in a cult someplace, doing strange things. So these bubbles have always been isolated, pretty much isolated, in a sea of power, fear, ego, and greed. So how do you explain love when people are about ego and power and fear and greed? It's a very hard thing to explain. So what happens is that these bubbles tend to be overcome by the apathetic to hostile environment. So if they're expanded, like many of the early religions were, if they start to expand, they generally get diluted at the same time. And or they just die out, or they remain in the margins. We've had philosophers, religions go back 4,000 years that said, this physical world is an illusion. What's important is love. And, we've had this has been around for a long, long time. And it's still around now. But it's in the margins. It's not a world sentiment. It's not in the mainstream. It just hangs out in the margins. And that's where it has always been for the last 4,000 years. Okay? The dominant cultures just overwhelm it. Okay, for example, the message that love or compassion is the answer didn't get us very far, or was dumbed down to metaphors and slogans, diluted by dogma, ritual, and beliefs. Because the idea was abstract philosophy instead of concrete science. And abstract philosophy is easy to dismiss, particularly when the high priests of our culture anyway, the scientists say, oh, that's a bunch of nonsense. You see? Okay. So the bigger picture has never been widely perceived as universal, coherent, rational, or scientific. It's always hung in the margins. But now, that's changing. So let's pull it all together. Scientists are now the high priests. It's their own experiments that are dragging them toward metaphysics. Other is metaphysics, not physics, you see. And for physics to say that other metaphysics is really the source, more fundamental, is a very hard thing to get them to say. The VR paradigm shift, the virtual reality paradigm shift, is gaining ground quickly, and other is close behind. We will probably see that before long, because I'm seeing this dash toward virtual reality among the physics crowd now. It's really become almost a stampede because it just solves so many problems. It's just better physics. Virtual reality is better physics, and physics people are starting to realize that that's the case. Okay? The unavoidable acceptance of the reality and significance of other, and it's unavoidable because, again, what, third grade logic? A simulation cannot compute itself. That's not a real giant intellectual step to come to that conclusion. That's going to rupture the boundary between physics and metaphysics. And this could be traumatic globally. Probably will be traumatic globally. Scientific models that join physics and metaphysics at the hip are coming available and better known. Okay? And I'm very hopeful that the scientific models that I'm talking about will successfully be able to compete against massive regression into faction versus faction belief-based dogma, each faction wanting exclusive ownership of other. History tends to repeat itself until its lessons are learned. So now, in the present, okay, contains the big picture bubble locally. Now it's different. We won't have the bubbles of enlightenment are not so easy to contain anymore. See, we have something new in the mix. Okay, they're no longer going to be isolated. There's no longer nobody to talk to. There's no longer, no models to turn metaphysics into physics. So what's the last piece? That's the internet. Okay, internet's going to allow millions of individual low entropy bubbles to interact, combine, support, and reinforce each other, while the local factions, the belief-based factions, struggle among themselves. Okay, so that is not necessarily going to happen this year or next year or even a decade or 4 or 5 decades from now. I don't know. Maybe that'll be 100 years. But the infrastructure is now in place that all of these little bubbles have reinforcement. They connect. You're here today. The reason you're here today is most of you got here through the internet. You see, if there was no internet, you see, I probably wouldn't have sold more than 10 books, in the last decade. It's the internet that does that. Because when I went to publishers, it was like, we need to fix that. I think we could cut that down into about a quarter of what it is, and you don't seem to be able to tell whether you're really touchy-feely or science, and we need to go one way or the other. And it was obvious that they didn't get it. They didn't know what it was about or why it was like that. So I ended up self-publishing just so I could control it, because those who wanted to control it had not a clue what it was about. So the internet made that possible. Without the internet, you have to get by the ogre at the bridge. And in my case, it was the big publishing houses. You can't do that. So the internet now is the last thing that'll let all of these bubbles encourage each other, come together. And I think now we're starting to build kind of more of a consensus all over the globe that things are changing. I always hear people say, well, don't you think that, this idea that love is the answer and the bigger picture is growing? I just feel that it's getting more and more people are getting involved in it all the time. I hear that, and that's true, because we've just finally got the infrastructure that will support it. Those little bubbles don't get snuffed out so easy anymore because they've got an internet. You don't have to go through the big publisher to get public. You see, so that's the difference. And now that we have that, see, for the first time in history, all the necessary pieces of the consciousness evolution puzzle have come together to enable a major paradigm shift away from fear and toward love. So this is a very exciting time to be. We're at the beginning of this. Okay, and this result will happen. And I say that with lots of confidence. Why will this happen? Now, I'm not saying it will happen quickly. It may be 1,000 years. We may self-destruct first and have to, start over at the caveman level. But eventually, it will happen. Why? Because it's on our evolutionary path. This is what we do. Look in the biological world. Remember, we had the individual cells had to get together and cooperate, and they had to cooperate in cell differentiation, different functions, within a body. And now here we are up at this level, and what is it we're supposed to do? Get together, cooperate, build something bigger, a bigger structure. And does that mean we become just a wheel in a bigger cog? No. You see, we're not just cells. We're individuated units of consciousness. We still retain our individuality. We still retain our free will. We make decisions and choices. but we care about other, you see? So that's another fear. The fear is that if we cooperate to form something bigger, the fear is we'll just become a cog in that big other machine. We don't want to do that. We want to be rugged individualists. But you can still be yourself. You can still be that individualist and still care about other and still work for a cooperative venture. So that's where we're going. That's how evolution works. That's the nature of evolution. It's got a goal, lowering entropy, and it keeps chugging to get there. So whether it's next decade or the next millennia, you can't tell. That depends on a lot of things. But this is where we're going to go eventually. And for the first time in history, all the infrastructure to support it is in place. And it hasn't been up till now. So all of these bubbles of enlightenment from the last 4,000 years forward are all in the margins because they didn't have something cohesive to pull them together. Because if you take these hundreds of millions of little individual bubbles and put them together, now you've got something that can change things. As long as they're all apart and don't even know about each other, you have something that's very ineffectual. So I find it very encouraging that in our evolution and with our technology, we finally got to the point that the last piece is in. Now we can do it. Now all we have to do is grow up and be able to do it, to lower our own entropy and grow up that spiritual growth, quality of consciousness, and the result is going to be one day that love will be the answer, and humanity will be form structures and ways of interacting and being that build and construct and persist, and everybody's talent, everybody's ability will be optimized. So that's where we're going. And after that, you can imagine this thing continues to grow. Then it won't be just humans and, of course, all the things on the planet. It's not just about humans. All the things there's lots of conscious things besides humans. But we're kind of in the lead of this march now. It's the human period, right? So we're in charge of this march. And when we get our thing together here on this planet, now maybe it's going to be planets all over the place that'll have to learn to be cooperative and work together. And then maybe galaxies all over the place that'll have to learn to cooperate and work together. You see, we got a lot of growth in this thing, but that's just the way this evolution works. That's what it's going to end up. We just need to grow up to the point that we can do it. We can make it happen. Those little cells just needed to hang out together long enough that they could figure out cooperation, produce better results than just being on their own, everybody out for themselves. But they did it. We're doing it, but we have awareness. We have an advantage. It shouldn't take us 500 million years to figure that out. Hopefully we're smarter than a bacteria. We can figure it out. We're probably more destructive than a bacteria too. But so there's a lot of hope. So I leave it, this is kind of at the end of this part, and I leave it with a very positive note that this step of becoming love is, in the long term, inevitable. This is where we're going. It's because evolution won't quit until we go there, because that's the nature of consciousness evolution. There will always be this urge, this nudge in that direction. No matter how much back we fall, we will work our way back up and go there. And now we have the infrastructure to support it. Yay, team, right? Good. Okay, that's the talk. Now I go have one other thing. I have one more. I thought I was done, but almost done. Okay, so we have all the ingredients. How do we make it happen? Okay, remember there's a few things to not forget on your path. If it's not your truth, it's not your experience. If it is not your experience, it's not your truth. You have to own it, right? You have to be it. This is not an intellectual exercise. You can't just learn about it and say, oh, right, I get it, I see. Love is the answer, that's good. That won't help. maybe that will help a little. Might make the place a little kinder. May make your behavior better, but we're not trying to improve behavior. We're trying to improve the quality of the individual, and then the behavior will improve all by itself. So you have to change at the being level. You have to get rid of fear. It's not about an intellectual process. It's a process of becoming and of being, and you can't do it at the intellect. You have to grow up, not just talk and feel like you've grown up. Okay. As always, it's up to us. No one else will do it for us. Growing up and living in a bigger picture has never been more important. And growing up and living in a bigger picture has never been more accessible or easier. Because now we have logical scientific models to provide a more universal map. All these bubbles before, they all had their own map, and they all had their own poetry, and they all had their own ideas, and they all had their own dogmas and so on eventually. So even the bubbles fought with each other, right? The bubbles of enlightenment, weren't maybe as enlightened as they thought, and they fought a lot with each other. So now we have a more universal map. And that's an interesting thing. And it's not just me when I say we have, scientific models. There's other scientific models. This is the only one I know of that is universal, but there's lots of models, and eventually they tend to coalesce, and that will take place. But even in this model, what's interesting is the universality of it. You see, there are lots of people who are atheists who find this model to be superb. They like it. It suits them as atheists. See? The larger conscious system is this natural, evolving system, there's no dogma in it. They like it. And there are many people who are very devoutly religious, very seriously religious, and they love this model, see, because they see the larger consciousness system is finally the rationality, for God they always knew were there, and they really weren't all that wound up in the dogma anyway, you see. So you have something that appeals to the atheists as well as to the theists. You have something that appeals to, East and West. This is science. West loves science. You see, it's the Western culture that has the high priests of science, not necessarily the Eastern culture. The Eastern culture has a different culture, but what I've told you, you can find in Eastern culture. The way it's translated now into science fits the Western culture. So you see, we don't have cultural divide. Atheists, theists, West, East, rich, poor, educated, uneducated, it doesn't matter. It's more of a universal kind of thing that people can relate to because it gives them a structure in which to base their own personal experiences. Some survey that I've recently read said that something like 85% of people who were randomly interviewed have had some personal paranormal experiences. The sense of being a bigger reality than what we think, what we see with our senses is very widespread. But they have these experiences, and their first idea is, am I going insane? What is this? It was a strange experience, and I'm afraid to tell anybody about it because they'll think I'm nuts. That kind of thing. Well, here's something that tells them, oh, that's just the way it works. Science will verify that kind of experience, you see. So it's a more universal, less divisive bubble than we've had before. So I see that as these various scientific models end up changing and coalescing, any model that's a live model changes. This will no doubt change and grow too. And others will change, and maybe bits of others will get adapted to this or this to others. It really doesn't matter. The point is that now we've got an understanding that is more universal, and we've got a communication system that is nearly universal, and there isn't anything but good that can come of the marriage of those two.